Hey YouTube, how do we distinguish sounds? I mean, to you and me, it's obvious that this is a nice pleasing melody, and this is not a sound you want to hear in the middle of class. But is it possible for a computer to algorithmically determine these sounds? Can a computer say, well, that's the quack of a duck? Well, that's a problem that professionals are still struggling with, not to mention for myself to tackle. But what I can do is solve a similar but surprisingly easier task: distinguishing the voices of humans. The basis of my algorithm for distinguishing voices lies in the Fourier Transform. Now this is a pretty complicated formula, and they teach whole college classes on it, but I'm going to do my best. This is your typical audio recording.
What the sigma?
Now if we graph the volume of that signal over time,
What the sigma?
we get something that looks like this. Your typical audio graph, right? Now this is also an audio recording. This time of a pure tone. And its volume graph looks like this. Now you may be wondering, if it's a pure tone, how come it goes up and down so much? Well, that's because the sound we perceive is actually based on how fast the volume changes, known as frequency, and not based on the volume itself. For example, this tone is also a pure tone, but since it vibrates faster, it sounds higher, aka the pitch goes up. However, if the sound we perceive is only based on change in volume, then does the volume itself mean anything? The answer is, well, volume is volume. These two waves have the same frequency, but since this one is bigger, we perceive it as being louder. But what about different instruments? I mean, the same note on the piano sounds different from the same note on the violin. Sounds different from me singing this note. That's what we call timbre, or the quality of a sound. Notice the unique triangle shape of the piano, or the more complicated curves of a violin, and the big peak followed by two smaller peaks in the voice. Interestingly though, by adding many pure tones, we can create those more complicated noises. For convenience sake, I put all the tones into one graph, and adding this combination in particular results in the violin's noise. Now if I simply change the volume of different sine waves, so the same pure tones are here, all I have changed is the tone's volume. This slight change in composition results in a clean triangle, like the piano's. This is the basis of a Fourier transform, taking an audio wave and splitting it into pure tones. Graphing the frequency of each tone on the x-axis and the volume on the y-axis, we get a new but equivalent way of viewing the signal called the frequency domain. This graph, for example, tells us there's a bunch of 440 Hz tone in the violin note and some higher tones as well. The frequency domain in general gives us a new perspective on the signal. Okay, so that was a pretty lengthy explanation of the Fourier transform. But now that we have that out of the way, we can get to the fun part of making a computer algorithmically determine voices. But how can we make a computer recognize voices? Let's say I record a voice line and I want the computer to recognize it's my voice. Well, the first step is to apply a Fourier transform so that we can get the frequency domain of my voice. Next, we simply compare it to all the voices in a database and see which one matches the closest. Pause here to see if you can figure out which of the 8 clips on the right the voice on the left matches to. If you said the third one, maybe you should get your vision checked out, because there's no way these two look anything alike. Having 2 clips look similar though isn't very helpful to a computer anyways, so what we really need is a mathematical definition for similarity. And a few weeks ago, Mark Rober happened to release his latest video on puzzle robots. What does a puzzle robot have anything to do with voice recognition? Well, just like I need to compare 2 curves, Mark Rober needed to
find the puzzle piece that had an edge spline that matched up perfectly.
And what did he do?
We would overlay the splines and then calculate the area between the 2 edge splines. So 2 pieces that were obviously not a fit would have a lot of overlapping area, whereas 2 pieces that were a perfect match, the overlap area would essentially be 0.
I realized I could use the same idea for my algorithm. Just instead of comparing puzzle lines, I would be comparing voice lines. Now that I have a complete theory for how a voice recognition algorithm could work, I got to building it right away. The first thing I needed to do was compile some test data. So I asked a few of my friends to record 6 voice lines each, and voila, now we have a bunch of data to use. For each of these test files, I applied a Fourier transform, so all of our signals would be in the frequency domain. And now, using the area comparison that Mark Rober mentioned, we can get a similarity score for my voice line to every other. As you can see, my voice matches to a Wesley voice, which is my name in case you haven't figured that out yet. Now, the accuracy of this thing is okay, just around 75%. And that is in fact better than guessing, because if we're guessing, it would only match 1 in 8 times, or 12%. But 75% is still not particularly useful or practical at all, and I know we can do better than that. So there's 2 fixes I want to try. First, restricting the frequency to a smaller range, and second, removing the background noise. Since human speech is generally below 500 Hz, we don't need to consider frequencies all the way up to 20,000 Hz, which is what my system measures out of mouth. But actually testing this, I found 3000 Hz was a better cutoff because female voices tend to be higher, and therefore a boundary of 500 Hz would not be very equitable. In fact, if you have Alexa, you might know that its first version had to be completely redesigned because it wouldn't listen to female voices, having been trained by an all-male engineering team. Secondly, let's get rid of noise. A common technique to do this is simply squaring the graph. Think about it this way. When we square a fraction, it gets smaller. When we square an integer, it gets bigger, right? So when we square the actual signal, which is much larger than the noise, we can effectively reduce the noise while increasing the signal. And voila! Now it works, with a shockingly high accuracy in fact, 97.777%. In fact, it only got one of the 40 clips I fed it wrong, and it happened to be the shortest clip where the guy just said 3 words. And that's the whole voice recognition algorithm. Not too complicated, right? All we needed to do was take a Fourier Transform and compare it to voices in the database. So, what are the applications of this thing? Well, to be honest, not much. As far as an internet search goes, I couldn't find anyone else who had done anything similar like this. And there might be good reason for that. The only application I could think of was something like, "Hey Google, what time is it?"
It's 3:25 p.m.
But they seem to have that already figured out. But even if the application of my device is limited, there is one thing I can say in confidence. Watch Mark Rober videos because you might just stumble upon a solution to a problem you've been having. Thanks for watching. Subscribe if you enjoyed the video. Get out of here.